Hi guys, this is a video I just want to share with you quickly. It's called How to Spot a Misleading Graph and it's by Ted Ed. Alright?
A toothpaste brand claims their product will destroy more plaque than any product ever made. A politician tells you their plan will create the most jobs. We're so used to hearing these kinds of exaggerations in advertising and politics that we might not even bat an eye. But what about when the claim is accompanied by a graph? After all, a graph isn't an opinion. It represents cold, hard numbers, and who can argue with those? Yet, as it turns out, there are plenty of ways graphs can mislead and outright manipulate. Here are some things to look out.
Okay, so this is the reason I want you to watch the video. We're learning about graphing right now, and it's really important to understand that when you do not do graphs accurately, you can lie to people. You can actually straight up lie to people using graphs. Even though everything in the graph is true, you create the wrong idea for people. So they're going to show you some examples of how that works.
In this 1992 ad, Chevy claimed to make the most reliable trucks in America.
Look at this. Look at how much better that Chevy truck is than that one at the end. I can't even read what it says. I mean, it's such a better truck, right?
In this graph. Not only does it show that 98% of all Chevy trucks sold in the last 10 years are still on the road, but it looks like
All right, I'm going to pause it there. How many of you can spot the problem with this graph? How many of you can see why this graph is a bad graph?
Twice as dependable as Toyota trucks. That is, until you take a closer look at the numbers on the left and see that the figure for Toyota is about 96.5%. The scale only goes between 95 and 100%. If it went from 0 to 100, it would look like this. This is one of the...
That's really different, isn't it? Now you can see that while Chevy is slightly more dependable, it's not significantly more dependable than any of the other trucks in the graph, right?
Most common ways graphs misrepresent data by distorting the scale. Zooming in on a small portion of the y-axis exaggerates a barely detectable difference between the things being compared. And it's especially misleading with bar graphs, since we assume the difference in the size of the bars is proportional to the values. But the scale can also be distorted along the x-axis, usually in line.
Okay, so remember we've talked about this. The y-axis is the one that goes up and down, and the x-axis, the one goes side to side.
Graphs showing something changing over time. This chart showing the rise in American unemployment from 2008 to 2010 manipulates the x-axis in two ways. First of all,
Okay, so when we look at that graph, we can see that unemployment is just steadily rising. Like there's no changes. It's getting worse and worse and worse.
Scale is inconsistent, compressing the 15th month span after March 2009 to look shorter than the preceding 6 months. Using more...
See that? So between March and June, it's 15 months, and between September and March, it's 6 months, but it looks like it's the same amount of time. That's crazy, isn't it?
Consistent data points gives a different picture.
Wow, look at how that changes when you make the lines in the bottom reflect more proportions about the way things work. So that's a crazy kind of connection there, because now you can see that unemployment isn't actually rising very much anymore. It's holding fairly steady.
With job losses tapering off by the end of 2009. And if you wonder why they were increasing in the first place, the timeline starts immediately after the US's biggest financial collapse since the Great Depression. These techniques are known as cherry picking. A time range can be carefully chosen to exclude the impact of a major event right outside it. And picking specific data points can hide important changes in between. Even when there's nothing wrong with the graph itself, leaving out relevant data can give a misleading impression. This chart of how many people watch the Super Bowl each year makes it look like the event's popularity is exploding.
Yeah, look at that. Wow, more people are watching the Super Bowl every year. That's amazing.
But it's not accounting for population growth. The ratings have actually held steady because while the number of football fans has increased, their share of overall viewership has not. Finally, a graph can't tell you much. Overall view.
So what this is the orange line is just how many people are watching, okay? And you can see there's more people watching all the time. The blue line is the percentage of the population that's watching, okay? By percentage of the population, it means that maybe 2 out of every 10 or 5 out of every 10 are watching the Super Bowl. And as you can see, that hasn't changed very much. The percentage of the population isn't changing. So the reason that one line goes up and the other line holds steady is population is increasing. We know that. There's more people all the time. Okay, so obviously if there's more people, there's also going to be more people watching the Super Bowl. So what we're really wondering is if the more people that are watching the Super Bowl, if the Super Bowl has actually become more popular, or whether more people are just watching the Super Bowl because there's more people who are alive. And what we can see from the blue line is that the Super Bowl has not become more popular, there's just more people alive.
Membership has not. Finally, a graph can't tell you much if you don't know the full significance of what's being presented. Both of the following graphs use the same ocean temperature data from the National Centers for Environmental Information.
Okay, so this is a big error that we can have when we're doing graphing, and that is give information that doesn't actually have any meaning. Okay, in other words, information exists in the world and has context around it. That was the same problem with the Super Bowl graph. The information exists in the world, it doesn't exist just by itself. So we have to understand what's happening in the world around it in order for it to make sense. Both of these graphs are 100% accurate. But what matters is, what does this actually tell us?
Why do they seem to give opposite impressions? The first graph plots the average annual ocean temperature from 1880 to 2016, making the change look insignificant. But in fact, a rise of even half a degree Celsius can cause massive ecological disruption. This is why the second graph, which shows the average temperature variation each year, is far more significant. When they're
Okay, so what it's saying is small changes on this particular graph are really important. Sometimes small changes aren't very important. Sometimes they're very important. So knowing what the data is being used for, why it exists, that's really, really important.
As well, graphs can help us intuitively grasp complex data. But as visual software has enabled more usage of graphs throughout all media, it's also made them easier to use in a careless or dishonest way. So the next time you see a graph, don't be swayed by the lines and curves. Look at the labels, the numbers, the scale, and the context, and ask what story the picture is trying to tell.
Okay, so that's the end of the video. So remember, graphs can lie to you if you don't do them correctly. And that's why when I'm asking you to make graphs in math class, I want you to be really accurate and precise in the way you make your scale, in the way you do your numbering. All of those things really, really matter. You can't just throw things up in any kind of way that you want to. You have to be accurate and precise in the way you do it. All right.